Cobalt glass. Straight run viscosity too, 90, 50, 25. So that'll be a good starting point because the viscosity will be in the middle of the road. All right, so go ahead and get to the position on the door and torch. Usually you can straight the torch right after I pull from the furnace, and then I'm going to start pouring right here, and I'm just going to, so the torch usually it's best to stand back here, and I'll just pour 3 sets of 3, probably 9 here, and then 3 down the side right there, and this is where the crucible will be stacked. So you'll just sort of come in from the side with the lit torch and just heat the bead of glass as it leaves the crucible. So that's the idea. All right, so we're pulling L9 from the middle. A little closer, you're going to want the blue part of the flame to be real close to the bead of glass. Good. And then heat the part where the glass just came off until it flattens in. All right, so then the stamp, get ready. It's not quite there yet, but right about there, you'll want to it's all right. You can stamp it. Go ahead and press it in. Bottom edge there. That's good. Yep. Cobalt's the worst for radiant heat because it's so dark. It actually is very effective at radiating the heat. I find that putting on a rubber glove does help a little bit if you want. Otherwise, it's just kind of a quick and move away there. So that's the way it's going to go. With the torch, one thing that I've found is about the best posture is to angle it about like this. That way you can get in close and kind of protect your hand from the heat. But if you need a glove, I've got some gloves over there for if and when you feel so inclined. It's about 50-50. Sometimes people do, sometimes people don't. All right, so the next one's going right behind it. So right there, that's a nice dark blue glass there. So we're pulling from the left. So this is a lower flux, 90, 40, 25. So we'll see what 10 grams less sodium flux does. Watch the diameter after the pour, and also watch the thickness of the bead of glass. It should change. And this is a half-load chromium glass, right? So
yes.
M9 is our composition. All right, so let's go for that. Go ahead. That's not good.
Is it going to break?
Yep. All right, I hit that string there. And work on that string on the edge. So heat on that side to make the string melt. Over here on the side. There you go. Keep hitting that. Keep hitting it. All right. So then you can move in and stamp it now. It'll once it gets brittle, it'll break up. Okay. Now that looked like it had a little bit of unmelted batch. So unfortunately, that one's going to blow up. Now, the good news is that we have probably about 20 minutes or so. But
oh, that's scary.
Well, all I have to do is just put a beaker on it, or I could even go ahead and move it back. That sometimes gives it thermal shock right at the beginning. But any defect like that just has a way of making places where the tension isn't shared along the crystal lattice, or not the crystal, the amorphous bonding structure. Makes a weak point. So as the tension loads up as it cools, it focuses that and causes it to break. So what that often is caused by is a chunk of flux that doesn't get completely broken up when you stir it. I think that happened last time too. So it does happen. I'd say about one out of every group. These things happen, so we'll still be able to collect the color, and it'll probably break that side off. So
should we get a beaker?
I guess I'll go grab a beaker quick. So I'm not going to cover it quite yet, though. We'll have that for later. All right. Next up, we've got N9. So this is a straight run 90-50-25 for viscosity. So standard batch. And it's no color. Is that right? 09.
N9.
Oh, N9. I'm sorry. We've got 0.2 for chrome, 0.5 for copper. So chrome, copper. N9. So pulling from the right list. All right. Chrome, copper. Go ahead and really melt that in. Looks good. Okay, that's good. Piece just flew there. These will stay hot for quite some time, so do be careful. What you're hearing, starting to hear, is called crazing. The ceramic has a different coefficient of thermal expansion than the glass. So as the glass is shrinking as it cools, and so is the ceramic, it puts tension on the thin layer of glass. And every time you hear that little, tinkling symbol there, that sound, it's a new crack forming in the piece of glass. These are already completely crazed in the little checkerboard pieces you can see, and these are on their way to getting there. So crazing is what that is called. I think I might go ahead and move this piece back. It's probably, it could shatter as I move it, but we'll see how lucky I feel. I give that a pretty high probability that it's going to crack. 85% chance. 89.6% chance. So it's just the way it is sometimes. All right, so we'll re-pour that one. So, or a different one in that spot. So next up is 09, and this one is essentially I see what it is. We've got a low sodium, high calcium, right? That's what you guys did. So it's clear, so no color, clear glass. So, all right. So then really hit that bead to heat it up and make that pull in. That looks good. Now go ahead and stand it. Yeah, nice and clear, and you can see it does have a smaller diameter by a little bit. So we'll see how that pans out. Yeah, I was looking for, I guess he's hanging out back there, hiding behind the camera. I'm like, this is your glass, man.
Yeah, I filmed it.
Okay. That's why I was looking at you funny. So, okay. So that was O. Next up, we've got P9. So this one is a little high on sodium, a little 5 grams higher on calcium. Ooh,
oh, there it went.
There it went. Ooh, that's what I told you. Yeah. Aren't you glad I put that beaker on there?
Very.
Now, the neat thing about it, though, is that it's not a total loss. You know, this now is called cullet. It's crushed glass, and you could remelt that, and we'll still be able to get color observations, but we probably won't be getting any diameter observations. I should have measured that already. But we'll still put that in a beaker, and that way we can still do the color part of the observations. So, all right.
Oh, we missed it on film.
Oh, the breakage. Yeah. Sorry.
People at home will know what happened.
Yeah, they'll know. I'll know. I don't think we've got any yet. Yeah, nobody's currently watching. I'm mostly just capturing. I didn't announce this one. I'm just trying to capture it so we can review it later. So it hasn't gone viral yet, but just wait. I'm thinking here in a few minutes, it's really going to pick up. Okay. P9 is a copper manganese, so purple and blue. Right? So I'm pulling from left side. So we'll pour this one right there. Okay. Ooh, it's lower viscosity for sure. See how easy that poured out?
Mm-hmm.
Look how thin the bead is.
Making me thirsty.
Oh, yeah? That's like the Grinch, right? He eats broken glass. I don't know about molten glass. Yeah, that behaved a little different than I expected. That's upside down. Well, we'll figure it out. I'll put a typical label on there as well eventually to make it easier to read. There's also some interesting behavior of hot glass and color. And that is the color during the cooling process sometimes changes. It's called the striking of the glass, or the striking of the color. At what temperature does the color strike at? So what happens is, if you first pour it, it might look black or brown. It then transitions maybe at 600 degrees or so, 700 degrees, to a different color, like chrome does this. It goes through a dark brown and then a bright green. So some glasses exhibit some unusual color behavior. My glove's starting to come apart. That's interesting. But we'll see. So that's a copper mirror of reduced copper from the torch. And when we pick that up later or put it on the light table, you'll be able to see through it and see a different color than the copper. But it's carbon monoxide in the flame pulling electrons from the copper and reducing a little bit of metallic particulate copper is what that copper mirror is that you see on the glass. Kind of a unique thing for anything that contains the copper in it. All right. So next up we have Q9. So this is a high calcium, and it's a copper manganese again. So was that a match pair?
No.
No? Okay, it just happened to be that way?
Happened to be that way.
Because we did have some groups that collaborated. So this should be similar to the previous one, but much lighter in color. So that'll be a nice contrast. We'll see what a lower copper load will do. So we'll pour that one right there. Great. So far, that looks like a grayish, more grayish blue, purplish blue. Interesting color pair there. This one I think is going to transition a little bit the color. If you look at that rim right there, we'll see how it changes over time. All right, it's progress. So next up, we've got R9. So that looks like a straight for silica, sodium, and calcium. And then it's an iron manganese, high iron manganese. So I've tried that before. Next week, when we go to Cardinal Glass, they'll talk about Rouge. Iron oxide, they call it Rouge. It's how much iron oxide they add to the batch. That's what makes a normal window pane glass. If you ever looked on the edge, you'll see a little bit of a green color. You ever noticed how if you look on the edge, it looks kind of green, but it looks clear this way. What that does is twofold. Number one, it makes the heat distribute a little more evenly in the furnace. Number two, it makes the glass in the window more UV resistant. The iron does a very good job of absorbing ultraviolet. So that way it's better for our eyes indoors because we don't have UV light. But for instance, Cardinal Glass during the 2008 slowdown economically, they transitioned to a clear glass with no iron, super clear glass for solar panels. Because in that case, they do want the UV to get through to their collection. Energy collection. So they ran a low iron glass for that purpose. All right, so I am forgetting where I'm at here. So S will be a iron glass. No, I was about to pour R, wasn't I?
Yeah,
R, yes. Middle. Talking about iron. Close to each other. They're stuck on each other now. I guess it is Valentine's Day. I'm stuck on you, literally. Isn't it sweet?
Well, as a droid once said,
What?
If you watch Star Wars 2 Attack of the Clones, where the battle droid's head gets welded onto C-3PO's body,
Okay.
it says, uh-oh.
Okay, I'm stuck on you.
That's
Okay.
one we'll do.
Yeah. I haven't seen that part. I've seen lots of the older ones though. Must be one of the newer ones.
Yeah, it's one of the prequels.
Prequels. All right, so next up we have composition S, which is somewhat similar, except this one does have far less iron. It's iron only. So this will be it's kind of a light iron color. So we'll pour that guy right here. I'm pulling from back to left. There's my glove smoking. Yeah. Toasted? Yeah, feel free to use one of those white gloves over there if you'd like.
Do we need another pair of tongs?
No, it just is a matter of getting to the right temperature before it breaks, and then you gotta break off the piece. It's just some glass is a little more elastic. Different temperatures. Trying to get that too close to the rearrangement there. So, all right. Just move a little bit. Next up is T9. This is a chrome copper, and this might be one in a set. Maybe it looks like it might have coordinated. Chrome copper T and U, 0.3, 0.04, and then 0.5 and 1. So fairly low chrome copper. Got several of these, so we'll be able to do a nice comparison there. Anyway, this is T9. So the purpose of the torch, as you probably know, but I'm going to reiterate, is to try to eliminate as much of that fiberglass as you can, because the fiberglass is the most likely thing to get stuck in your finger or have some problem with. So that way we can handle this once it cools and be relatively safe. I have had one of these things blow up in my hand before.
Really?
Yeah, it's surprising. When I was holding it, it kind of hurt the inside of my knuckles. It was kind of like I got mildly hit with a hammer on the inside of my knuckles. I was holding it like this, and it was like shattered. So it was a unique experience. It didn't really do anything except hurt my knuckles. But these things can blow up randomly up to a year later. I had one go off a year later, just sitting in a cabinet. What was that? Open the door, glass everywhere. So they're unpredictable.
Crikey.
Yeah. All right, we've got three more. U9 is next. Go ahead. Of course. All right, so we got 2 more to go. So we'll put those back piece. Back a little bit. Sweep up a little bit of that glass. Catch the camel hair on fire. We'll see. How you feeling? Sure enough.
Does it smell?
Yeah, that's the burn. It's burning the hair. Yeah, I used to take a little bit of water and put a little dot of water on this so you can see how it's boiling. Then you could cook on this. This is about like a stovetop right now. But a little droplet of water hit one of the pieces of glass and cooled a little spot in the center, and it just shatters, goes off. So I don't do that anymore. I just burn camel hair on it. It's awesome.
Yeah.
So we'll pour one right there and one right there for the final 2. Should probably adjust my angles. That'll work. So V and W, just like the car. Remain. Ready. So we'll say for this last one, it's a little bit trickier with the torch. Try not to get the torch on the already cooled glass. That can do bad things. It wasn't enough that time to create any problems, but this last one's going to be tricky. So I'd say try to angle it towards this one that we just made and not towards the others. And that one, forgot to call. What was the composition? That one was high flux and only manganese. And it does look noticeably bigger in diameter, so that translates to the high flux, so you'll be able to measure that later on. So one more. And this one is normal viscosity or diameter, and another chrome copper. That was popular this time. Wow. Chrome copper, last one. Take it around that little button that just came out of the tray. There you go. That looks good. Yep. Great. Way died. Congratulations. So at this point, we've got a little bit of time to wait. So I'd say go back and you can finish up your crystals, and then I will prep the, well, that's nice to say. Very good. But I'll prep the videos so we can watch those. So we'll move on to the next part. Thank you for your help, for those that helped out.
At least we didn't have to call Station 51.
Yeah. Didn't have to call any fires there. Or triage.
Well, how nice they tell it.
They did jump out of this.
So the crystals can go into their respective collector bins over there on the far bench.
If you were to do the problem with experiment over again, what would you change?